let's get started. Number one, force. When you were little kids, you learned a definition of force, and you know what? That definition is good enough. Force is a or a What are those two words? Thank you very much. It's a push or pull. It was good enough for you in third grade, and it's good enough now. A force is a push or a pull. I like it being a push or pull because it lets you know, hey, this is what a force is. You exert that thing on something that we call a force. I like the fact that it's a push or pull because it reminds us that force is a vector, that force has direction. There's a difference between me pushing you away and drawing you into a warm hug. Let's keep going. Aristotle. At the time of Aristotle, he wanted to collect all of the knowledge that mankind has and bring it all together in one place. You tell me, where is that famous place, that famous library where all the knowledge of the world, of the known world, was brought together?
The Library of Alexandria?
Yes, sir. The Library of Alexandria, exactly. And it provided, there was the source of knowledge for mankind for centuries, until there was some stupid war and they blew it up or burned it down or whatever. But until then, it was awesome. Aristotle. Well, at the time of Aristotle, he collected the finest minds on earth, and they were able to describe why things move the way they do. There are 4 elements, correct? At the time of Aristotle. Anybody watch, The Last Airbender? What are the 4 elements? Good. Air, water, fire, and earth. Okay, great. The 4 elements. Let's say I have a rock, and I'm holding the rock up, and then I let the rock go. Which direction is that rock going to go?
Down.
Down. Why? No, not gravity. Because the rock is made of rock, and the earth is just one big rock, and this rock wants to be with that rock. Like wants to be with like. Rocks want to be with rocks, right? That's why it goes down. Let me ask you another question. I've got a bunch of hot smoke. I'm smoking a cigarette or I'm doing incense. So I've got hot smoke. I've collected it in a little container, and then I open the container up. What direction is that smoke going to go? Up. Why does it want to go up?
Because it wants to be with the other air.
Thank you, because it's air and it wants to be with air, right? That's not that difficult for you guys. I don't know why you're not getting it. But yeah, air wants to be with air. Let me ask you another question. Suppose I have water, 2 water droplets, and they get closer and closer together. Pretty soon when they touch, what's going to happen? Ooh, they're going to merge, right? Because water wants to be with water. Why do we have rivers and lakes? Why isn't water just evenly, finely distributed over the entire world? Why does all the water collect together in rivers and lakes?
Because water wants to be with
Because water wants to be with water. You guys okay with that? That's how they described why things are the way they are. Things want to be in their natural state, and their natural state is to be at rest with others of like. Okay? Let me ask you another question. The natural state of things. Look around this classroom. In what state is everything in this classroom right now? At rest. That's the natural state of things, is to be at rest. In fact, and now I'm going to, I don't get that. No, that's okay. I'll use this one. Okay. I'm going to put this guy in motion. What's required to make this chair have motion? A force. But eventually, it comes to rest, because that's the natural state of things. And so the thinkers back then, I don't know if I can call them scientists per se, because they weren't doing the scientific method, but the thinkers back then thought 2 things. Number 1, the natural state of all things is to be at rest. And when I say all things, I mean all earthly things. Heavenly bodies follow their own rules that I'm not going to get into. But the natural state of all things, I guess I'll say earthly, all earthly things, is rest. That's their natural state. And if I want something to have motion, I need to exert a force on it. A force is required for an object to be in motion. force is required for an object to have motion. If I wanted this chair to continue in motion, what would I have to do? Keep pushing the stupid thing, right? So a force is required for something to remain in motion. That's what people back then believed for centuries and centuries. And then Galileo comes along. And Galileo says, okay, if I have a ramp and I have a ball on that ramp and that ball is rolling down the ramp, that ball is going to go faster and faster, right? As it rolls down the ramp. And if I have another ramp like this, and I roll the ball up the ramp, then that ball is going to go slower and slower. Which means if I have a ramp that's completely horizontal, and I roll that ramp on the I roll that ball on the completely horizontal ramp, and there's no friction, there's no other forces happening here, what's that ball going to do?
It's going to keep on going.
How many people think it's going to keep rolling forever? Yes, that's what Galileo realized. It keeps rolling forever. It's going to stay in motion forever. Because this chair doesn't stop because its natural state is to be at rest. Why does this chair stop?
Friction.
Friction, right? And so Galileo's going, hey, if there's no friction, that ball's going to roll forever. So he directly contradicted what all thinkers thought before him. The natural state of all things is to be at rest? No. The natural state is to be in motion, to remain in motion. A force is required for an object to have motion? No. It is the force that makes it stop. If you don't have a force, it will remain in motion forever. You see that? No force means it goes on forever. Not a force is required for an object to have motion. The absence of a force is required for an object to remain in motion forever. And so one day Galileo died. And then shortly thereafter, that year, the year in which Galileo died, Isaac Newton was born. Which conclusively proves reincarnation is true, right? Because Isaac Newton took all of Galileo's ideas, which were really his own because he's just the reincarnation of Galileo. Galileo died and then he waited somewhere, wherever you have to wait, and then he ends up becoming Isaac Newton. And he devised 3 laws of motion. 3 laws of motion. And the first law of motion, he just took what Galileo said. He didn't even think of it himself. He said, my first law of motion is what Galileo discovered.
Sorry.
And here's Isaac Newton's first law of motion. He says, an object in straight line constant motion will remain in that motion unless a net force acts on it. An object in straight line constant motion will remain in that motion unless acted upon by a net force. Okay. Now, there's another choice for the motion of an object besides straight line constant motion. What other state could this object be in?
At rest.
Yeah, at rest. And so Isaac Newton also included that. He says not only is an object in straight line constant motion going to remain in that motion unless acted upon by net force, but an object at rest will remain at rest unless acted upon by a net force. So I'm going to use my pink marker because it's not just the straight line constant motion, but also an object at rest will remain at rest unless acted upon by a net force. Oh, are you done?
Yeah.
Wow, you're fast. Good for you. That means you got an A plus probably. Hey, you got a couple of them right. At least the ones I can read. Okay. What did I want to say about this? I can't think. I lost my train of thought. So let's talk about being on a bus. So here's the bus. Okay. Here's me. I'm standing in the bus. I was seated, but then this nice old lady came along and she said, "Can I have your seat?" And I said, "No." But then I discovered there was like some gum on my seat and I didn't want to sit. You know, so then I said, "Okay, old lady, you can have my seat." So now I'm standing and the bus is going 40 miles an hour, right? And then the bus driver slams on the brakes. Tell me, what do?
You go 40 miles per hour.
Thank you. I continue going 40 miles an hour, right? I'm going to be going in straight line constant motion until a net force acts on me. What's going to slow me down?
The wind crashing into something.
Thank you. Crashing into the dude in front of me. That'll do it, you know, right? You know, or maybe I grab onto a pole or I do something, but something's going to have to stop me. The friction between the road and the tires is stopping the bus, but that's not stopping me. Something inside the bus is going to have to stop me. And if not, then I continue on 40 miles an hour till I slam into the front of the bus, at which point I stop because the front of the bus stopped me. You see, I'm going to continue in that motion unless acted upon by a net force. Here, let me give you another example. Now the bus is at rest. And I'm standing, like the subways, if anyone did the Science Olympiad trips, the subways that take off with an incredible acceleration. So let's say I'm on the subway, alrighty, and I'm standing, and then the bus takes off really fast that way. What am I gonna do?
40 miles per hour. Go back.
Yeah, I'm gonna go back. But am I really going backwards? What am I actually doing?
Staying at rest.
Yeah, I'm remaining at rest. It is this guy that's moving. This guy's moving that way. I'm remaining at rest. And so it just looks like I'm going backwards. Actually, I'm remaining at rest. It's the subway car that's going forward out from under me. You see? There's a name for this tendency of me wanting to maintain my same state of motion, whether I'm at rest or in motion. Do you know what that word is?
Inertia.
You guys thinking inertia? Yes, sir. Inertia. We have inertia. Now, let me put it down here. Inertia. An object's tendency to maintain its current state of motion. An object's tendency to maintain its current state of motion. Object's tendency to maintain its current state of motion. Yeah. Now we're going to learn later when we learn about mass versus weight that actually mass is the measure of an object's inertia. That is, some objects can have more inertia than other objects. For example, compare me and Imani. Let's say both of us are at rest. Are we both going to resist changes in our motion equally? Or is one of us going to resist changes to our motion more? Who's going to resist changes in motion more? Me, right? Because I'm so much more massive than she is. which means it's going to be a lot harder to get me moving. You see? So we can measure inertia, and we use mass to measure inertia, but we'll talk about that later. So inertia is an object's tendency to maintain its current state of motion. Okay, so hey, thus ends my introduction. So tell me, what does Newton's first law of motion say? Or let me ask it this way. If I want to change the motion of an object, what's required? Yeah, a force, a net force. Good. Tell me, what do we call an object's tendency to maintain its current state of motion? Good. Okay, and that's it. That's all I got. So thanks a lot, guys.